Welcome back, green chemistry students. Today we're going to have a brief presentation to enhance your knowledge on life cycle assessment, and in particular, the idea of using a chemical tree. Remember that this information is required and will be helpful for you in designing your own chemical tree as part of your life cycle assessment exercise. That'll be part of your course assessment. In the life cycle assessment online material, you would have seen in your reading the idea of the word chemical tree, and we are not really accustomed as chemists thinking about the chemicals in terms of it coming from a particular starting material, which if we trace back all the way to its roots, we can see it looks very much like a tree. The leaves, the fruits, our final products, those are connected to branches, of course, branches because they are processes, raw materials, and systems that make those products. But then those processes, raw materials, and systems also come from other processes, raw materials, and systems. And if we continue to move backwards, eventually we'll get to the roots of the tree. And in most chemical processes, you would see once you design a chemical tree, you figure out what the chemical tree for that product or process is. You will understand that the roots of the tree, based on our current scenario of how we use and derive our chemicals, our fuels, our materials, what we consume, a lot of it goes back to oil and gas resources. And that's why we say we have an oil-based chemical economy. And we'll be seeing a little bit of that in the example that we're using today. This slide shows a reaction network, a network of chemicals which can be made from a starting material that's called furfural. Furfural itself is part of the Sustainable Chemical Production Trust. And in terms of sustainable chemical production, furfural is called a platform molecule. It's a platform because we can build many types of molecules in chemistry off of it. We'll be dealing a little bit more with this when we look at module number 4 and the biorefinery concept. So from the slide, you can see that there are several routes leading from furfural. We will be looking here today at the route that furfural is converted to furan by decarbonylation, that is taking off a carbonyl group, and then by selective hydrogenation to give us tetrahydrofuran, which is an important chemical in terms of it being a solvent for many plastics processes, but also being used to make resins and plasticizers that are important industrially. Tetrahydrofuran can be further hydrogenated with ring opening to give us butanol, which is also an important solvent in its own right. Now, tetrahydrofuran has been made before the modern times of trying to do sustainable chemistry in different ways. This particular reaction scheme is a classic scheme that is quoted in all the papers that deal with biorefinery concept. But before that was the case, tetrahydrofuran was made by malic anhydride hydrogenation. This was a patented process, and the same company that patented that process also patented furan hydrogenation. You've seen the furan hydrogenation route there, albeit they use different types of materials to accomplish that. And in hydrogenation, you're well aware that we need hydrogen for it, and we talked a little bit about hydrogen in our previous lectures. Now, the modern process that is now, I suppose, taking over the older processes is butanediol dehydration, which some claim is a greener, better process, more sustainable, more environmentally friendly. But of course, all of these sorts of alcohol dehydrogenation reactions require us to have strong acids, which you would know about from your first year chemistry courses. So these are the industrial routes to THF, and at some point in the future, we can look at the greenness of these processes. But for now, what we're really concerned with is the chemical tree, and in particular, understanding where we get those raw materials from. So this is a classic chemical tree. It's taken from your textbook, where tetrahydrofuran is the product. So that is the gate, and that is on your left. And for each strata below it, before it, you see that we're going backwards in time, backwards in processes, backwards in synthesis, like a retrosynthetic analysis that you do in your organic chemistry, where you know that your tetrahydrofuran is coming from furan and hydrogen, which we showed in the reaction network. But then each of those chemicals are also coming from another resource. So for example, hydrogen is derived from natural gas and water. But of course, they have oxygen there by steam reforming, which you'll cover in industrial chemistry courses in some detail. Furan is derived from furfural and calcium acetate industrially. So that's furfural calcium acetate. And of course, calcium acetate is then derived from calcium hydroxide and acetic acid. And water, the place where we get calcium hydroxide from is not a naturally occurring material, so we get it from limestone, that is calcium carbonate, for example. Acetic acid is by the Monte Santo process, so we get that from methanol and carbon monoxide. And then we could go back a step. Where do we get the carbon monoxide from? Where would we get methanol from, etc.? So in each of these steps, you can see what are the inputs for those steps. And of course, there would be associated chemical reactions, chemical processes, systems, reactor systems, industries that will be built around each of those steps. If you look at furfural on this chemical tree, furfural comes from corn. It can come from all types of sugars, all types of lignocellulosic biomass, but particularly in this case, industrially from corn. And you can use sulfuric acid to dehydrate the corn. There's a hydrolysis reaction to take the sugars and break them down to give us furfural and other things. And in each case, if you go backwards, all the way now to the right, you see that the raw materials come back to being petroleum extraction of the petroleum refinery, that's oil and gas resources, water, air, natural gas. Again, these are the basic resources. Of course, limestone comes from the soil. So in the strata, that is number 4, you can see limestone there, that's coming from the soil itself. In strata number 3, you can see that corn is a raw material and that is biomass. So if you were to look at this process, you have to go all the way back to corn production, limestone production, petroleum production, water cleanup, natural gas production, in order to understand all of the inputs, outputs, all of the associated environmental issues, pollution, waste, inefficiency, catalysts, auxiliaries, atom economies, etc., in order to get a full picture of your life cycle assessment. So this is really very useful in mapping out your final product, which is your gate, all the way back to its cradle. So the chemical tree allows us to go back to the cradle when we're at the gate. We can identify reactions and processes that need to be redesigned, since we know exactly what those processes are. We can identify raw materials that are high risk, since we know what all those raw material inputs are and have low sustainability indices. We can talk about and think about pollution reduction, since we would have each of those processes mapped and therefore know the yields. You can look at the atom economies, apply all of those green metrics. We can talk about waste reduction bottlenecks. So that's when we're trying to reduce waste. Where is the waste? What is the waste? How are we going to redesign? You can also use this to have allocations. See, where can you allocate a particular impact to? So for example, if we were looking at the furfural to tetrahydrofuran process through furan as the intermediate, we can easily allocate the associated impacts with corn production to agricultural process, or with petroleum refining to petroleum refining process, as opposed to putting that as part of our life cycle. This also helps us to understand, to change, to move around the boundaries to match our goal and scope in our life cycle assessment. What we must remember, of course, is that we need to consider the end of life of these chemicals. Are they biodegradable? Are they designed for degradation? Are they hazardous? Not only from the cradle to the gate. What happens when we try to recycle them? Are they recoverable with efficient processes, etc.? We see also in the chemical tree lots of numbers there, and those are the actual numbers that come from the processes, the industrial processes themselves, or alternatively, in your case, when you do your assignment, from your chemical reactions and working out using your moles and your theoretical yields. So this chemical tree is very beneficial to the chemist in understanding exactly what outputs are coming out of your system in terms of life cycle assessment, those environmental indicators, what they would be, where would they come from, and also what are the inputs that you have to put in. What you have not looked at or mentioned here is the fact that you would have as well energy inputs which are not noted on that, and that's where the rest of the life cycle assessment, the input, the inventory input would come from.